So, multiple regression. So already we have discussed what is multiple linear regression is. It's nothing but when I try to identify a relationship between two or more variables. You have to always use multiple linear regression, or you can say this is one of the very simplest method to identify the relationship between different variables. So always when we have a lot of variables, we always uh, be having a group of independent variables and a dependent variable, right? So in simple linear regression, we have one independent variable, one dependent variable. Whereas here we have multiple independent variables which are kind of associated with one dependent variable. So the equation for multiple linear regression is given by y equal to beta naught plus beta 1 x1 plus beta 2 x2 until beta p xp plus error. Okay. So here beta naught is but nothing but your intercept, and beta 1 is your coefficient of the variable x1. Okay. Beta 2 is the coefficient of the variable x2. So here x1 and x2 are your independent variables. Okay, it can be any number of variables. That's why we just have, a final variable is p. So p can be 10 or 15. Okay, so this is our model for multiple linear regression. So this formula only we will be able to compute dependent variable. You can, for example, you're trying to find the price of a house. So x1 can be the width of the house, h may be the number of rooms, x3 will be the you know um, number of bathrooms. Something you can just go on. So you can include any number of variables to find out the price of a house. Okay, so multiple linear regression is used to identify a continuous variable. Okay. So least square method. This is one of the methods used to find out the best fit. Okay, for this regression problem. So when you say the best, it's actually kind of found out by minimizing your sum of residuals. So you will be having an error. Right, when we compute the multiple linear regression. So this least square method is help to find out your y by creating a best line by minimizing your error. Okay. So I mean, when you say line of best fit, it also looks like, for example, you have the sales and temperature in your x-axis and y-axis respectively. So we can see sales of it. Cool drinks increases when the temperature increases. Okay, so the data is not completely linear, but we can able to find a best fit line by minimizing our error term. Okay, so this is our line of best fit looks like. Okay, next we will be looking into polynomial regression. So polynomial regression is actually a regression method where we are trying to fit a relationship between the dependent and independent variables as multiple linear regression. Here, the major difference here is using a higher order polynomials. For example, so when we have a multiple linear regression, linear regression for two variables, you just have y equal to beta plus beta x. Whereas here, you just have only one independent variable ex, but here formula for second order polynomial is y equal to beta naught plus beta 1 x plus beta 2 x squared plus error. Okay, so here you are having a second order polynomial x squared. Okay. Whereas for the second order polynomial for two variables, we have beta naught plus beta 1 x1 plus beta 2 x2. X2 is your second variable plus beta 1 x1 square of your first variable, beta 2 into x2 square of your x2 variable, and then beta 1 to x1 into x2 plus e, your error term. Okay, this is your formula for second order polynomial for two variables, and this will be like, progressing for your third order variable. So it's not like you can have higher order polynomial until like k whatever term. It is not possible. Actually, you always have to minimize your higher order polynomial. Okay. So usually we have this beta 1, beta 2, right? So here beta 1, beta 2 are your coefficients, but it's the beta 1 is because of your linear effect. Beta 2 is a coefficient because of your quadratic effect. Okay. So when you have a kth order for your polynomial model, so the formula here is like you have your beta naught plus beta 1x plus beta 2x squared, and if you are like having a third order, beta 3 plus x cube, beta 4 plus x to the power of 4 until it goes on for beta k x to the power k plus error. So this is how your kth order polynomial model looks like for only one independent variable. Okay, the equation looks like this. So in a linear regression, we'll be having a straight line, which able to like fit the data. But here in the polynomial regression, you will be having a curve line, a curve. Okay, so for curved linear regression, we can say we will be using polynomial regression. Okay, so here the equation is y equal to 5 minus 2x plus 25x square. So beta 1 is minus 2, beta 2 is 25, and beta naught is 5. Okay, so here the x y is increasing, and over a period of time, y is increasing. Okay. So as I said, this polynomial models are used when you have a curvilinear relationship between the two variables. And as I mentioned already, the order of the models should be like, always less as possible. For example, if you have an order of greater than 3, you should try to avoid it, and trying to like reduce your polynomial through order of n minus 1, because it's always possible. You can always able to reduce your model to have a good fit to your data. It is always possible. So always you have to have a order of like 1 or 2 is the best model. Okay, so this model building can be like carried out through forward selection or backward elimination method. So this is, I think, a very important strategy used in what is it in the regression methods. Okay, so forward selection is a method where you will be like adding each of the variable one by one to create a regression model. Whereas in backward elimination, you will be like trying to eliminate a model one by one based on your p values. Okay, we will discuss this right now. Okay, so the stepwise regression is otherwise called as backward elimination. Okay, so this is one of the very important method used in the regression, where you can able to automate your linear regression process. Sometimes you'll be having too many variables in your data, and you don't know what are the variables to include. You can't just include all the variables which is available. Okay. it is not needed. You have to really find out what are the variables are making sense to this data. Okay, so this can be like identified through stepwise regression. Okay, this stepwise regression helps to like drop the insignificant variables. Okay, so we'll just see that one by one. So we have the p-values for one of the outputs. Okay, here it is 0.0. It is here for the other variable it is 0.092 and 0 for all the rest of the two variables. Okay. So just imagine here we are trying to create a model with too many variables. Okay, so we have all our independent variables here. Okay, and we have our p-values here. So when you just look into p-values, the highest, you can just take the highest p-values here, and your adjusted r-square is 0.7. Okay, the highest p-value is this variable, 8th grade math, 0.89. Okay, so we found out this the 8th grade math is the highest p-value, so we can eliminate this variable out of the model. So, and then when we eliminate the 8th grade value, the adjusted R square is kind of decreased. So, sorry, increased. It was like 0.733, and now it is 0.74. So now what is the highest p-value? So here we have household income, which is 0.89953. Okay, so we can eliminate the household income. Okay, now our adjusted R-square becomes 0.7485. Now we have the highest p-value for the obese column. So we can eliminate that. Okay, so when we eliminate, our adjusted R-square becomes 0.75. Next, the highest p-value is population. So we can eliminate population. When we eliminate population, the answer is 0.75. So here we have the IQ's p-value is 0.5. We can eliminate that as well. So here our value is increasing to 0.76. And the next highest p-value is 5 vegetables. Okay. Again, the adjusted R square has become 0.7631. So here, guys, please understand, I'm just showing a random example with a very good example for this stepwise regression. Okay. When we remove that variable, adjusted R square becomes 0.7578. Okay. So again, we are removing the highest, p-value variable. We got the answer 0.7525 for the adjusted R square. Again, we are removing one more variable. Okay, so it is, see here we got by removing one of the variable we got 0.7631. So we here checked, okay, region NE has the highest p-value, so we remove that. So even when we remove that, I think we didn't remove that, but since even after removing the final other variable, there is no increase in the adjusted R square. So when that happens, you can just finalize your model. So this is our final stepwise regression model. Okay, so we always have to try to eliminate the variable which has the highest p-value. Okay, so this is actually a very good method to find out the stepwise regression. Okay, So before employing this method, you have to look into the multicollinearity as well, and also you should be able to find out the correlation between each of the variables with the dependent variable. Okay, so that is also a step that you should be following. So first, maybe you can just try to create a model with all the variables, and then you remove one variable at a time, and then you create a reduced model with by looking at the p-values, and then if the p-value is kind of greater than your significance level, you can still remove it. Okay? So if you want, you can still remove one of the variable here, but logically, if you think that value contributes more, and you need that variable according to the the business knowledge, you can keep it. Okay, so you can just repeat this whole procedure until you get a p-value which is less than your significance level, or there are no variables in the model for which p-value is greater than the significance based on the partial F test. Okay? So until that, you can keep on removing it, and then you can get to a final stepwise regression model. Okay, the stepwise regression is a combination of forward selection or a backward elimination procedure. So in forward selection, actually you will be starting the model with no variables at all, but you will be calculating the correlation between the dependent and all independent variables, and then you develop a cynical a linear regression model by adding the variables for which the correlation coefficient is highest. So if one of the variable is having a very highest correlation coefficient than the rest, we'll be adding that particular variable to the model, and then you keep on adding one by one according to the coefficient, correlation coefficient, but you can add the variable if only when there's a corresponding p-value is less than the level of significance. Okay, so you'll be creating the model, and then you'll be conducting a F test to check whether the variable is statistically significant at the alpha, and then you will be adding it and completing the model. Okay. So hope you had a very good understanding on how polynomial regression works and stepwise regression works. We can get into the sums, but if you got any questions, you can ask now.